I just wrote the new website name, which is easy to remember, dss.mit.edu. So I invite you to use that. We also post the videos online, so you can use them for later if you miss a talk. And for today, I will leave my co-host, Dr. Carolina Osorio, to introduce our speaker and welcoming the transportation talk of the term. It's the first one, actually.
Of the term, yes.
Of the term.
Of the first DSS transportation talk of the term. So it's my pleasure to introduce our guest today, Professor Serge Hoogendoorn. He is currently a distinguished professor of smart mobility at TU Delft, the Technical University of Delft. And this is a distinguished professorship appointment that only 4 faculty across TU Delft have. And he's also, from the last few months, also department head of transportation planning at transportation and planning at TU Delft. He holds the chair in traffic operations and management and leads also a cluster in coordinated and cooperative, however that is pronounced, traffic management. He's PI for also with the Amsterdam Institute for Advanced Metropolitan Solutions, of which MIT is an academic partner. And he's a leading expert on initially traffic flow theories as applied to vehicular traffic, and then extended also to pedestrian traffic and bicycle traffic, with work in dynamic traffic management for all of these different modes, and also worked extensively in evacuation modeling. His theories have developed both fundamental theories using innovative sensing and data collection techniques, as well as really creative field experiments. He's very well known for a lot of his pedestrian field experiments, and now also doing really exciting work on cycling experiments, of which I learned one is taking place tomorrow, where they have a whole sporting arena reserved, and people are just going to bike around to actually see whether the data actually validates some of the theories, fundamental traffic flow theory that he has developed in his group. He holds several honorary professorship positions, one of which is listed here, Monash University, and of course, faculty at TU Delft. He has co-authored over 200 journal publications and has edited or been co-author of over 9 scientific books. And he's led a variety of major research projects, including an ongoing, very prestigious 5-year ERC, or European Research Council project, looking into specifically fundamental traffic flow theories for cycling and pedestrian traffic. His methods and ideas have had a very strong impact, of course, in transportation science, but also in transportation practice and engineering. A lot of his work looks at how do we deploy some of the really neat ideas that are coming out of transportation science in the field. And he's worked very closely with major agencies to both develop these innovative concepts and also to deploy them in the field and see successful deployments. So thank you, Serge, for taking this invitation, and I'll leave the floor to you.
Okay, thank you so much, Carolina. And Lydia, for having me. Very honorable that I can be here, so again, thank you a lot. It was 20 years ago we just established that I was here the last time, so it's been overdue. Again, I'm going to ask the question I asked before. Who in the room is in transportation and traffic? Oh, that's almost everybody. Oh, that's good. So for you, there's going to be little theory today. So I hope I'm going to show you some things that you don't know yet. I'm predominantly going to talk about some of the more applied things of our field, and you will generally see that in Delft, that's some of the things that we're very proud of. We're trying to not only think about science and engineering, but we also try to take our ideas and bring them to practice. And some of the examples that I'm going to show to you today are doing precisely just that. The title of the talk is Making Mobility Smart Again. You figured out that was a bit of a pun. But it does revolve around this idea that it's not just about new technology and new data. It's also about putting these data and these new technologies in a smart way to practice. And for that, we need knowledge. Right? And that's essentially what I'm going to talk about and hopefully convince you, as far as you have not already been convinced yet, that our field, transportation and traffic theory, is a very important field to make solutions work. So just as an introduction, this I don't have to tell you, right? The societal urgency of the things that we're doing. I looked up Boston in the TomTom congestion index. You're not doing well. Well, you're doing well because you're rising up, right? You're getting to the top 10. But as you can tell from the slide, the average delays that you're experiencing on a daily trip, a commuter trip, is around 13 minutes, which is quite substantial, right? And actually the numbers are increasing, as you can see from this graph over here as well, with 3% compared to last year, right? Next to this, of course, it's not only about accessibility, it's about the environment, sustainability, it's about safety, and all these different factors that are due to our transportation system not working in the most efficient and reliable way, the way that we want it to work. Well, if you look at these problems, these have been around for quite some time, right? And we also know for quite some time that building new infrastructure is effective, but not always a good solution. It's expensive, we don't have the space. So this is why, in my group, we've been mostly looking at, well, looking for better ways to use the infrastructure that we have. And that's essentially what I will be talking about for the remainder of this presentation, right? How do we use the the roadways that we have in an efficient way? So then the first question that you might ask yourself, okay, why would that work? And I have a very simple example to give you some insight for us so far. You don't know this already. Why, well, smarter use of the infrastructure that we have actually can make a lot of sense. And I generally use this, well, quite extreme example in the sense that we're talking about an evacuation. And obviously an evacuation will not happen all the time, but it nicely shows the different things that I want to talk about for this talk. And it's going to be a bit of an interactive talk, so I hope that I see hands raised and stuff like that to the stupid questions that I'm going to ask you. The example that I'm going to show you is the evacuation of a peninsula in the Netherlands. And we chose this peninsula because it has a very nice name. It's Walcheren, so the typical Dutch or pronunciation of the word, which has 120,000 inhabitants. And the idea is to try and see if we can evacuate them in time. There's a flood coming. The flood will last for 6 hours. And we're going to assume, which is, well, not a very realistic assumption, that these people are going to evacuate by car. And each car will, well, carry 2.5 people. Right? So that means that we want to evacuate 48,000 vehicles off the island in 6 hours. So that's the exercise that we're facing. Now, if you look at the island, so here we have the island, we have essentially 3 roadways out of the island. We have 1 motorway, which has 2 lanes. We have 2 rural roads, which both have 1 lane. For the sake of argument, we're going to assume that there's no lane reversal. We're just going to use these 4 lanes. Well, as you know, as traffic engineers, right, a lane has about a capacity of 2,000 vehicles per hour. So the total outflowing capacity is 8,000 vehicles per hour. That's no rocket science. Now, my question to you is, do we have enough time to evacuate all people? And that's not a rhetorical question. Who thinks we do? I should always reverse the question. Who thinks we don't?
With a little bit of variability, then someone has a problem. With a little bit of variability, someone gets left behind and dies.
Okay, so there's 1 or 2 people. We can. We have 120,000. Okay, so you're smart, as I expected. So what I would do, if I was a simple man, I would say, okay, if we look at the network and we look at the outflowing capacity, it's 8,000 vehicles per hour. We have 48,000 people. Well, you can do the math, right? It's easy. It's exactly 6 hours, right? But it turns out not to be the case. We didn't really trust this solution ourselves, so we did a more advanced simulation. We have a simulation model called EVAC that allows you to, well, essentially simulate the impacts of a flood or another type of hazard. In this case, it was a flood, which lasted for 6 hours. We actually found out that if we apply this model, that instead of these 120,000 people that we, with this very simple back-of-envelope calculation, were assuming to be able to evacuate, only 25,000 under the situation where we were not providing information to the people, or 41,000 when we were providing dynamic information to the people, were able to get off. So despite the fact that for many reasons you could expect, there is always a few people that are left behind because of small disturbances, the differences between what we were calculating beforehand and what we're actually simulating are obviously huge. And the question is, what's the reason? What's the main cause? Right? And you're already noticing some of these issues. Well, the main reason why this is something we observe is a typical property of traffic networks. And it has to do with the fact that once we start overloading the network, the performance of the network is severely deteriorating. If the loads are low, you have efficient self-organization phenomena, and this is just a cool example from Hanoi. You can say it's not very safe, but it's efficient, right? But once the load goes up, you see this phenomena in traffic that is actually severely reducing the efficiency of the network. The capacity drop, start-stop waves that essentially will reduce the capacity of your road with 30%. If the load is even further increased, you get phenomena like spillback and gridlock that further reduce the output of your network. Right? And this can be a good explanation for what we saw in the evacuation experiment. It all boils down, if you look at the different phenomena that we see, to a very simple relation that has been hyped a bit over the past, let's say, 10 years, the network fundamental diagram. Who knows about the network fundamental diagram? I think many of you have seen it, right? It shows an average relation between the average density in the network on the one hand, so the average number of vehicles per kilometer, or in this case per meter per lane, versus the production or flow in the network. And what you can actually see, and this is an example that we've determined ourselves using Google data from Amsterdam, that as long as the number of vehicles, the densities in your network are relatively low, an increase in the density essentially means an increase in the flow and the outflow of the network, which is a good thing. More vehicles in the network means more vehicles flowing out of the network. But you can also see that once the density goes up, there's some sort of a tipping point, a critical density, so to say. From that point onwards, you will actually see that the outflow of your network is going down, which means I have more vehicles in my network, but less vehicles are flowing out, right? A good example that shows this overall deterioration of network performance. What you can also see in this graph, and that's why I like it really a lot, is that there's huge differences between different networks. It can be caused by many things. The structure of the network. We found out that it's also actually to a large extent determined by the use of the network. Actually, we've been able to prove that not only the average density determines the outflow from the network, but also the spatial variation of this density. Using a very simple mathematical equation that we are able to derive analytically, showing what the impact of this spatial variation actually is. Overall, you see, the more heterogeneous density is distributed over the network, the lower the performance of your network is. Right. The cool thing is that this doesn't only apply to cars, it also applies to pedestrians. Right? So this is a very generic characterization of traffic infrastructure and the performance thereof. So let's take a look at pedestrians. Who knows a bit about pedestrian flow, except for Nigel, but he knows it because of me. Okay, another very simple example. An experiment, and as Carolina told you, we've been doing lots and lots of experiments with pedestrians and nowadays also with bicycles, trying to characterize these pedestrian flows, finding out in the meantime marvelous phenomena that are actually prototypical for these pedestrian flow operations. The example that I'm going to show you is actually something that we did not do ourselves. It was done by the Herms group. Pedestrians will come from the left, pedestrians will come from the right, for you it's just the other way around, and they will walk towards each other. It's actually quite a dense flow that you're going to see. What's going to happen? Who thinks it will be chaos? Who thinks it will not be chaos? Okay, what do you think?
People will naturally follow others and not one.
Okay, you've been looking at too many YouTube movies. You're completely right. So you have self-organized phenomena. In this case, the organization of dynamic lanes that actually turn out to be very efficient. Right? As you can see, and sometimes it seems to stagnate a bit, but you don't get complete chaos, you don't get blockages. You see that the flow actually self-organizes in a very, very efficient manner. If you would look at the capacity of this facility, it's a few percent lower than a unidirectional flow, but the differences are actually not as big as you might expect. Now the thing is that this will not work all the time. You will see that if the flow becomes denser, there's more people that are using the facility that are coming from the left and are coming from the right. There's actually a severe probability of the flow breaking down. If that occurs, I already talked about the capacity drop. The capacity drop on a freeway is around 15%. Right? This essentially is a capacity drop of almost 100%. Right? If the flow breaks down, and it happens somewhere in your network, you would essentially get a blockage in a specific element in your network, and congestion would spill over the network very, very quickly, potentially leading to very dangerous situations. I'm not sure who of you still remembers the Duisburg incident at the Love Parade, where many people died, essentially. That was because of the same reason. People wanted to get out, and many people wanted to get in at the same time, and because of the demand being so very high, there was no efficient self-organization, and it was this very, I would say, forceful packing of pedestrians that actually caused many people to die. Right? So this capacity drop idea for pedestrians is actually much worse than you would get for instance, cars. Now, the interesting thing is that we've been studying these phenomena, these traffic flow phenomena, very intensively. And based on that, we've been able to come up with very simple principles that will allow us to improve the design and the management of traffic networks and pedestrian facilities. And this is just an example of these 4 principles. I'm not going to go in detail. They're very, very simple, probably to you as well. It has to do with the prevention of spillback. It has to do with the better utilization of the capacity that you have in your network by distributed traffic, all the things that you probably already know. And again, these are not technical solutions. These provide you with a sort of underlaying sort of main principles that would allow you to come up with practical solutions for the different problems that you see in your infrastructure facilities and in your traffic networks, applying to both car traffic, to bicycle traffic, and to pedestrian traffic. And again, I'm not going to give all these theoretical principles. I'm just going to give you some examples of applied work that we've been doing, showing you how we've been essentially looking at data collection, state estimation, and data fusion for different types of applications, in this case, focusing on crowds. Amsterdam hosts an event called Sail. Sail is all about toll ships. So these beautiful ships that sail into the harbor of Amsterdam. And many, many people come into Amsterdam. Amsterdam is not such a big city as you might expect. Right? And they will look at these toll ships, they will enter them, et cetera, et cetera. So that's really a big event. It's hosted every 5 years and attracts many, many visitors. How many we don't precisely know. Right? The numbers that we see range from 1.5 to 2.5 million visitors over a 5-day period. And there's where it becomes complicated. Right? We don't know precisely how many people there are. So that makes planning for the event rather difficult. Right? So we have these wonderful principles. You can start thinking, using these principles for planning, but if you don't know precisely how many people are coming, that will become cumbersome. So what we've been doing is thinking towards, can you not do a reduction of the uncertainty in, for instance, the number of people that are coming and the design of the facility that you're doing by using real-time information on what is going on at the event. Right? So for instance, by identifying where the choke points are on the event site, where choke points are expected, where a situation becomes critically dangerous because the densities become too high, et cetera, et cetera. And then, well, for car traffic, that's something that we've been doing for years and years. But the question is, how do you do that for pedestrians? Right? There's a few systems that can actually correctly determine the situation, the crowding situation during such an event efficiently. So what we've been starting to consider is using different data sources. And what you will see is that none of the data sources that we've been considering gives a complete picture of the situation at hand. We've been using counting cameras, which provide you information at a cross-section on the number of people that are moving in and out of the facility that you're considering. But for instance, determining densities from these is a very hard task to do. That's not going to fly. So that's by itself not enough. We've been using Wi-Fi and Bluetooth sensors that for a small share of the people will tell you when the sensors are passed. That allows you to determine travel times, for instance. That allows you to determine the routes that people have taken. But it, for instance, doesn't give you any information about the density itself. Again, right. We've been using Twitter and Instagram. That provides you information on where people have tweeted, what they've been tweeting about. With some crawling, you can actually determine gender, age, place of origin, etc., etc. But that by itself doesn't also provide you with the information on the density and the crowdedness, right? Unless you trust what people are tweeting about. And finally, you can think of using apps, GPS. We've been working with a company called Woof that has a Find Your Friend app that provides information on the locations of the people that are using the app at a 5-minute interval to get a quite accurate position of a person for those people that are actually using the system. Right? By itself, none of these data sources gives us the information that we need. It's in the combination of the different data sources that we are finding that we can really make the difference. And this is just to give you a bit of an insight of the different types of information that we can then present to the people that have to manage the event. Right? You see the GPS locations, you see the locations where people are tweeting about crowdedness. You can actually see also from this graph, and it's very small, I know from the people in the back, the location or the origins of the people that are using social media. You get essentially the OD relation here by combining the counting cameras with the Wi-Fi and the Bluetooth signals. And you can actually get some information about the routes if you track the people that are using Instagram. And finally, by combining the data sources, we can actually say something about densities at different locations. Right? So in combining different data sources, we can really improve the quality of the data that we're providing to the users of this crowd monitoring dashboard. And that's actually where the knowledge comes in. That's why we really need to understand the nature of the phenomena that we're observing in order to give a good way to combine these different data sources. And you can do that in multiple ways. We're using models. However, most of the models that we've been developing so far are not really suitable. So the one equation, and this is the only couple of equations that I have. For those of you almost look scared or happy, I'm not sure. So this equation here shows our microscopic pedestrian simulation called Nomad. Right? It's based on game theoretical principles where pedestrians, on the one hand, try to get to their destination as quickly as possible. They want to do that without too many changes in their acceleration and direction. But they also don't want to be too close to other pedestrians, especially those pedestrians in front of them. Right? So if you do the game theoretical assumptions, if you do the continuous modeling, then you do some additional assumptions on the behavior of the other pedestrians, of the opponents, you get an equation that looks a bit like this. Now, I'm not going to explain it in detail, but what it essentially says is that I have the acceleration of a pedestrian, which is a vector, because it's a two-dimensional phenomena, that on the one hand is governed by this equation that shows that people have a tendency to move into the direction that they want to walk in, on the one hand, and they want to walk at a speed that they're desired to walk at. Right? So that's the vector v0. That's the desired velocity. So both the speed and the direction. And you see that there's some tendency to move towards that desired speed and direction. The second part of the equation shows you that people are repelled by other pedestrians, especially those pedestrians in front of them. Right? The R that you see, the capital R, essentially determines the distance from you with respect to the other pedestrian. Right? So this is how you can interpret the equation. It was developed by the experiments that Carolina was already talking about, right? We were in 2002, that's already quite some time ago, one of the first in the world that did these experiments. You can, if you look very carefully, look at the red hats that allowed us to very easily track the different pedestrians and get very detailed information on their behavior. Using these data, we're able to calibrate and validate the model equations and improve the model as we went along. The cool thing about this model is that it's relatively simple, but it still captures many of the phenomena that we see in pedestrian flow. So the self-organization you saw at the very beginning, if you look very carefully, you see in a crossing flow also you also see self-organization. You get these diagonal stripes that are moving through each other. All these phenomena are, at least from a qualitative perspective, but if you calibrate the model also from a quantitative perspective, predicted by this very simple model. So in that sense, it's a quite powerful model. Now the question is, can you use such a model, for instance, for data fusion or for Kalman filters? Well, our idea was no. It's a microscopic simulator. It will be very involved to use that, for instance, in a Kalman filter to fuse all these different sorts of data together. So we wanted to have a different type of model. We wanted to have a continuum model or a macroscopic model. So I think many of you know the LWR model or the kinematic wave model. We wanted to have a model similar to that in order to be able to use it in a Kalman filter style of approach. So the question is how to do this, right? Well, what we did was actually, in hindsight always, not so very complicated, right? First of all, we assumed equilibrium, which essentially meant that in this case we're assuming that the pedestrians have zero acceleration. This allows you to put the speed and the direction, so the velocity, on the, I'm now really having be bothered by the jet lag, on the left-hand side of the equation, and then get this expression. That's very, very simple. Still it's microscopic, right? So still you have all the other pedestrians and the interactions that you somehow need to include. What we then did is we interpreted the density surrounding a pedestrian, the average density, which is a continuum description of flow, as we interpret it as a probability of a pedestrian being at a certain location, right? So by doing so, you can actually come up with an average expression by integrating this term. It looks a bit like this. And there we have it, our macroscopic or our continuum model. We have expressed the equilibrium speed and the equilibrium direction as a function of this desired speed and direction on the one hand, and an integral that essentially expresses the influence of the density around the pedestrian. So that's completely macroscopic. Agree? Yes, good. It's also horrible because you have to integrate, right? And well, I'm really an engineer, so I don't like putting this into my models. It becomes way too complex. So we did something, well, very simple. We used a Taylor series approximation for the density around the pedestrian that we were considering. And then it became very simple indeed, because that allows you to do the integration in an analytical way, yielding two expressions. An expression for the equilibrium speed, which is in this case a function of the density on the one hand and of the density gradient on the other hand, showing that when the flow becomes denser, the speed goes down. Well, for those of you knowing the fundamental diagram, that makes perfect sense. And on the other hand, you see that if the density is increasing, the speed also goes down. There's some sort of anticipation, if you will, stemming from this approach to modeling. And at the same time, we have our equilibrium direction that people want to walk at, which is a function of this, well, desired direction. So you have a goal and you want to get there, which makes perfect sense. And again, the density gradient showing that you're shying away from groups of pedestrians where the density is high, and you move into directions where the density is lower, right? That combined with the conservation of pedestrian equation, for those of you again knowing the LWR model, this will look very familiar. Notice that this is a two-dimensional model, so there's the main difference. We have a complete model. How simple was that? You don't seem extremely enthusiastic, so it might not be that simple. The key thing is, we wanted to have a macroscopic model that kind of captures the different phenomena that we see in a pedestrian flow. And it turns out that if you use this model and you do some numerical approximations of the model, it's, well, I'm not going to say seemed, it looks like the model is able to capture, at least from a qualitative point of view, all the different phenomena that we saw in our experiments and that we saw in our microscopic model. Right? So we have this bidirectional lane formation. We have these diagonal stripes that you see in a crossing flow. We can actually also capture the fact that depending on how large the demand is, we get a flow breakdown. So from a qualitative perspective, the model seems to inherit the properties of the microscopic model. And the cool thing is that as far as models go, this type of model is definitely usable in a Kalman filter or another type of scheme that you would be using to either filter the data that you have or to fuse the data that you have. Does it work? Well, I have to be completely honest. We used a very simplified model in order to do something with our social media data. Actually, my student was stubborn. He said, I'm going to use Twitter data to give a proxy of the number of pedestrians in one of the links that we were considering during sale. And Twitter data is obviously biased, right? Because you're tweeting where things are interesting. He thought that using a combination of the Twitter activity on the one hand and a simple macroscopic pedestrian model on the other hand would allow him to come up with a reasonable estimate for the crowdedness at that area that you see in the animation. And it seemed that he was right. Right? So what you see in the graph, that's the blue line that you see over here, that's the quote-unquote ground truth data that we were able to get from combining the Wi-Fi data with the counting cameras. Right? Just inflow, outflow, and a correction because you know how long people have traveled in that link. This is one of the models that he's been using. The red line, although it is not completely continuous everywhere, is the approximation that he made using the flow-based model, which is very similar to the model I just showed you. And I was quite surprised when I saw this, because, okay, there's error, and you can actually also argue that the interval that he's been using is way too long for dynamic purposes. But the trend that he was able to reproduce is quite nicely following the ground truth. And this was for sale, this is for the King's Day, and it seems that the results are actually quite robust. The thing I wanted to show you how powerful the use of modeling, knowledge about the phenomena that we're trying to observe actually is, if you're trying to estimate the state as accurately as possible. Okay, that doesn't obviously only apply to pedestrians. We've been using similar type of analysis for instance, queue length estimation. In this case, the task was, because I'm not sure who of you has ever tried to estimate a queue. With loop data, that's a notoriously hard problem to solve, right? Because generally, we only have information at cross-sections. We know inflows, we know outflows, but because of drift, miscounts, and those kind of things, it's actually very hard to do. And that's a shame, because queues are very important in many of the approaches that we're using. Right? So if you, for instance, look at back pressure type of intersection control approaches, you need these queue lengths. Right? So how to do that? Well, we had the idea of using floating car data, Google data, or in this case, TomTom data, to kind of enrich the information that we're getting from the loops. The question is only how, because TomTom data in itself is wonderful. Essentially, we have travel times, but it's still very sparse. Right? Also, it has quite a substantial latency. So just getting the data sources together in a naive way will not work. So in this case, we've used, and I'm not going to tell you all about the details, what I've called traffic flow inspired machine learning approach, or a neuroscopic traffic flow model, whatever you prefer, to kind of combine the knowledge that we have from the process that we're modeling with some advanced machine learning technique. And what you can actually see is that although it's not perfect, if you compare the estimates of the Q for the intersection that you can actually see in the animation running above, that it's not perfect, but it's pretty well. It's much better than what you would get if you would just use the inductive loops. And actually, and that's a very important thing that we've been working on as well, we can show how much this improvement that we're making in the accuracy of estimating the Q would actually mean for our traffic management purposes, showing you that we can actually save around 100 vehicle hours per peak by this increase of accuracy that we're able to establish. Right? So similar problem as we saw before, using knowledge on the phenomena that we're trying to observe to improve the estimate using the data that we have, and in this case, fusing the data that we have. Okay, so then the second part, right? I gave you some information on how we're looking at state estimation, data fusion, using different sources of information. Crowds, cars, the principles are actually quite the same. Now the question is, now we have this wonderful idea on the current situation in the system, how can we use the technology and the information that we have in order to influence the system that we're going to consider? And then again, I would argue that naive use of the data is actually not the means to go forward. So you really also, for the control of the system, need to really understand how the system behaves and how it works. And what I want to do in the last bit of my talk, is the video already 5:45, is showing you some examples that we've been working at, showing you how knowledge of the behavior of the system actually can improve the application that we're considering. And actually the 4 examples that I'm trying to show you, if I have time, is the resolving the start-stop waves, wide-moving jams, they're also called. I'm going to say something about how you can use a network-wide approach in order to improve the effectiveness of measures. If I have time, I will say something about active mode traffic management. So these essentially are bicycles. And finally, I want to go back to the problem I showed you originally, namely the evacuation of Walcheren. And with these 4 examples, I'm going to show to you how you can actually use the knowledge of the system in order to improve dramatically the effectiveness of influencing the system by means of information, guidance, and control. Now, let's start with something that I guess everybody knows, variable speed limits. Who knows what a wide-moving jam is? Well, you're all traffic engineers, right? So wide-moving jams, as you know, occur when traffic is in a certain density. So if you have a homogeneous queue in which the density is high, the queue is unstable, and a small perturbation will actually become what you call a phantom jam or a wide-moving jam. Right? And this is a very famous video that shows this. I think many of you will know it. In reality, these things look a bit like this. This is obviously also reality. This is an on-ramp on a German freeway. You see small perturbations here that grow out into these wide-moving jams. Wide-moving jams that move in the opposite direction of traffic at a speed of around 80 kilometers per hour, being unsafe because people essentially don't expect them, but thirdly, also severely reducing the capacity of the facility with around 30%. Right? So getting rid of these wide-moving jams would be, well, really mean an improvement in the throughput of your facility. So how can you do this? Well, in the Netherlands, we've been using variable speed limits, I think since the 80s. I haven't seen them so much here. Is that correct? So really, well, you have speed limits, but these dynamic speed limits respond to the speeds that they're measuring underneath the gantries. Right? So if the flow drops down below 50 kilometers per hour, you would see that on the gantries, and the one upstream would actually show you that you're running into an area where the speed is actually quite low. So it would warn you. And the thing is that what we've been using essentially only provides information of what people can expect. Right? So it essentially warns people. Many assessments of these systems have shown that actually in terms of throughput, the impact is very limited. It's increasing safety, it's increasing the comfort of people because they really rely on the system. But for instance, in resolving congestion, in getting rid of these phantom jams or wide-moving jams, it doesn't do much. So the question is, can future technology help here? Can, for instance, in-car systems help you in improving the effectiveness of these variable speed limits? Well, many of the examples that you can actually see in practice, that using in-car technology, using the same type of ideas as were formerly on our dynamic speed limits. So nothing really changes in a sense, only the actuator changes, right? You get an in-car signal instead of a signal above the road. So how can we improve this? Well, a few years back, we developed an algorithm that we thought would be effective. And the system, in terms of its principles, is actually very simple. There's a catch, though, and that's the one thing I want to discuss with you. You see an animation here. We have the wide-moving jam, so traffic is moving into that directions. The red cars are actually showing the wide-moving jam itself. The idea that we had was, again, very, very simple. We're using speed limits to reduce the flow, and thus we reduce the inflow into the wide-moving jam. Right? If we reduce the inflow sufficiently, if we reduce this in such a way that the outflow of the wide-moving jam is larger than the inflow, the wide-moving jam would disappear. Agreed? Simple. Okay. Now the question is how to do this. And this is where the trick occurs. And again, you're traffic engineers, so for you this will be relatively simple. But I want to ask you a question. I want to ask you a question on how to deploy the speed limits. I'll show you three situations. The one without a speed limit. So the lines are trajectories. We have time here, we have space here. So these are vehicles that are driving at a certain speed and a certain time and distance headway. The first example shows a situation where you have a speed limit at a certain location. So people drive into an area where the speed limit has been reduced, right? So that's this thing. The second thing is a situation where all of a sudden you're deploying the speed limit over the entire or a large part of the roadway stretch, right? So you see this change in the direction of the vehicle trajectories. Now my question to you is, which of these two deployments of a dynamic speed limit will be more effective in getting rid of the wide-moving jam? And again, this is not a rhetorical question. Who thinks this one? Yeah, oh, you're alone, sorry. Who thinks this one? And the question is why? If you look at the picture. Density? Can you explain further?
The one on the left increases the density.
Yeah, and why is that good?
Or
bad?
Bad because it might induce another jam.
Ah, okay. Not the answer I was looking for, but any other ideas? And I kind of gave it away on the slide. Right, so this is the time headway of the entire platoon. So it's the duration that it takes for the entire platoon to pass. This shows you exactly the same, but then after applying the speed limit over the entire stretch. So in this case, the platoon only takes this amount of time. In this case, the platoon takes a much longer amount of time. What does that mean for the flow? The flow is not reduced in this case, right? Because the length of the platoon in time is exactly the same here as it is here. In this case, it's substantially reduced, right? Because the duration that it takes for the platoon to pass has increased substantially. So this is the trick. If you want to really reduce the inflow into the wide-moving jam, this is the way that you should deploy the dynamic speed limits. And this is essentially what we've been using in the specialist algorithm. Right? You can do all the math, but essentially, and this is real data, so this is something that stems from the pilot that we actually were doing on the A12 in Utrecht. If you look carefully, you see the wide moving jam. We determine the length of the wide moving jam, and then using this relatively simple formula, we deploy the speed limit over a certain roadway stretch of length L. Right? And by doing so, the flow is substantially reduced. The flow into the wide moving jam is substantially reduced, and in this case, it's dissolved. Actually not so complicated as long as you understand that you need to do that over that entire stretch in one go. And that was successful. It's successful if we deploy it, if this length can actually be catered for. So if we have sufficient roadway length to be able to get rid of the entire wide moving jam. If the wide moving jam is very severe, if it's very wide, right, then this L jam will be large, and this might be too large for us to control. Right? So this is why we actually only had 2.8 activations per day, and when we had an activation, we solved the wide moving jam in about 72% of the cases. That's still a relatively successful thing, right? Because if you just look at the total vehicle loss hours that we're able to save by getting rid of these wide moving jams, this very simple strategy, and you have to make an approximation or an estimation of the amount of wide moving jams that you would have over a year, and the travel time savings that you're making thereof, we are able to save about $700,000 US on an annual basis by just deploying the technology that we already had in a different way. Oh, that's not a bad thing. One question to you. What can I do to have more activations per day? So it's now only 2.8. So in 2.8 cases on average per day, the system decides that it has sufficient roadway stretch to buffer traffic.
Non-constant speed, upgraded speed limit.
Yeah. Why would it help?
It would reduce the length because you can make the rough markers slower. And
Okay. Yeah, actually, so we've been also, well, piloting with changing this, but I'm not sure if that's what you mean. But that would only increase the inflow into the wide moving jam. That can be sufficient, but if it does anything, it would reduce the effectiveness rather than improve the effectiveness. We've been considering coordination. We've been using other types of measures to temporarily buffer traffic. Right? For instance, you can use an on-ramp and ramp metering in conjunction with the variable speed limit control that we've been using. Right? It doesn't really matter where you store traffic, as long as you're able to get rid of the excess number of vehicles in a wide-moving jam. Now you might ask, this is cool, but this is old technology. Ramp meters, who works with ramp meters nowadays? Well, the road authority still does, but everything is smart vehicles nowadays. Right. Oh, sorry. Well, the cool thing is that this methodology and this line of reasoning can equally be used for smart vehicles. Right? So instead of just thinking of having platoons of vehicles that are driving closer together, you can think of how to control these vehicles to get rid of these type of phenomena. So not only having a capacity increase because you would reduce the time headway of two vehicles following each other with 5%, but getting rid of the wide moving jam and essentially saving 30% in capacity drop. Right? So the methodology is not different, the way that you actuate traffic is. And again, that's the key thing of my talk, right? It's about thinking in a smart way on how to use the technology that we have. Well, The question obviously then also is, okay, we talk about smart vehicles, but you're from the Netherlands. Everybody bikes. It's true, in Amsterdam, 54% of the trips that are being made by bike. That's wonderful, by the way. It's sustainable, it's healthy, it's good for accessibility. So what about these bikes?
The Dutch cycle more than any other nation in the world, almost 900 kilometers per person. But that also means we have 350,000 bike-related injuries. Now imagine that we would make biking safer, smarter and easier by applying self-driving technology to biking.
We taught our self-driving bike to figure out where it is, what's around it, what will happen next, and what it should do. We leaned on Google's expertise in self-driving cars, but we had to adapt the technology to work on a bike. We decided to add 2 additional features. First, you can request the bike to pick you up wherever you are, and we developed a comfort mode, adjusting the pedals to a perfect resting position.
I think the self-riding bike could really give a boost to the economy because people could also work on their bicycle. You work in your office, you work in your home, you work in your car. You could even work on your bike.
I have so much more time. My kids love it. They're just free. They can go anywhere they want, anytime they want. It's amazing.
At the Fietsersbond, we feel that this is the biggest invention since the invention of the bicycle itself.
At Google, we always put our users first. With the launch of this bike, we believe we do that again.
Okay, you got it, huh? That doesn't mean that we cannot do smart things with the bike. So actually in Delft, as Caroline already was explaining, we've been doing quite a bit of work to work on technology to improve the attractiveness of bicycling, right? For that, you really need to have more insights into cycling. And believe it or not, even coming from the Netherlands, where 54% of the trips in some cities are actually made by bike, the knowledge that we have on bicycle flow operations is actually very limited, right? So this is why we're currently doing these type of experiments. And this is a small version of that. We found actually the capacity drop for bicycles as well. What about that? To start thinking about, well, smart solutions for bicycle flow and bicycle traffic management. And one of the things that we're currently doing is we're actually equipping a bike. It will not be a self-driving bike, obviously, but with sensors and actuators that would allow you to communicate, to sense and communicate cyclists. Right? And the typical type of applications would be the joint optimization of signal control with dynamic speed limit advice in order to get some sort of a green wave for cyclists. And our simulation experiments already show that in doing so, we can have a severe reduction in the number of stops, which for cyclists obviously are very annoying, with about 45%. So this is really, for a bicycle-heavy country like the Netherlands, very, very relevant. But it might also be relevant for you, right? Because cycling is potentially a key solution to many of the issues that we have, right? Space is scarce in cities. Cities are getting denser and denser. And it's a bit of a shame that you use half of the space that you have in your city for transport infrastructure, right? And bicycles actually can, to a certain extent at least, provide an excellent solution for this. They make use of the space that we have much more efficiently, next to the fact that given the increased attention to objectives other than accessibility, like livability, health, sustainability, right? The bicycle can actually also have a very important role. Let's see if we can get Boston up to 54% of trips by bicycle. That potentially is not going to happen, but it does show you that especially in the light with all these new types of services that we have, mobility as a service, shared services, e-bikes, autonomous vehicles, etc., etc. It might be the good time to start rethinking about what you really want your transportation system to do, right? It's not a battle of the modes, it's really about the optimal mix of the different modes that you have at your disposal. So, a call to arms in a sense. Don't only think about cars, but there's other opportunities as well. So I'm going to skip this. I'm going to do one final bit, if Carolina will allow me. So the trends that you see in terms of technological development really make that our field is super exciting. At the same time, you see many trends from a more societal perspective that essentially mean that we might need to rethink the objectives of our transportation system, right? It's not just about accessibility anymore. There's other things that are at stake as well. And one of the trends that you also see is that the resilience of the system is becoming more and more important. This, for instance, had to do with the fact that the number of extreme rainfall cases is dramatically increasing. And apparently people do a bit silly things in case of a flood, right? So that doesn't only mean that the system can be severely disrupted, it also means that the chance of a real flood becomes more substantial. And now we'll close the loop with looking finally at our evacuation problem. Looking what we can do by optimization of the instructions. Recall we had 120,000 people with a voluntary evacuation where we essentially said to people, well, figure out yourself what you want to do. It was this 25,000 people that we were able to save. Providing people with the information that you have on the traffic operations in the network, providing them with the shortest route, in that case, yanks up the number to slightly over 41,000 people that you can get off the island. Right, so still, and I think you all know what the reasons for this are, that's a low share compared to the 120,000 people that we're trying to get off. Optimization, on the other hand, turned out to be very successful in this case, right? And I know I've been working in traffic management for a long time. If we have 5% improvement, we're already happy. In this case, we were able to get, well, twice the amount of people off the island by using a bi-level formulation and optimizing the evacuation instructions in terms of when people were allowed to leave and which route they had to choose. So this shows you that there's room for improvement in supporting evacuation instructions. However, it's robust, but it's not super robust. There's many uncertainties in this case. There's uncertainties with respect to the hazard, right? You're never sure which dike breaks and where it breaks and what the breach will be and how quickly you would have the flood spilling over the island. There's uncertainty with respect to the behavior of the people. Will they comply to your instructions? How would they behave? It's robust, but you do see that if you would, well, change the scenario a bit in terms of the flood or in terms of the behavioral response, you get a reduction in the efficiency of about 5 to 20%, right? So that's not too bad. However, it does mean that we're also looking into other types of support, not in the planning phase, but in the operational phase, and that's the last movie I'll show you, and then I'll shut up, right? So dealing with unpredictability by providing real-time support for traffic managers during an evacuation. So that's actually the next challenge. It will be about state estimation, not only for the traffic flows, but also for the water levels. Right? It will be about prediction, using the models, the combined models of the transportation system, the multimodal transportation system on the one hand, and the flood modeling on the other hand, and the interaction thereof. And it will be about decision support. Piloting in 2018, so somewhere at the end of the year we have some first results. And I'm super keen on showing you this at another occasion. This is what I wanted to leave you with. So I think the main takeaways, smart solutions, it's not only about data, it's not only about technology, it's making smart use of these data and these technologies using traffic engineering knowledge. And with that, I'm going to give the floor back to Carolina. Thank you so much for your attention. It's not too bad, is it?
Question to hand wave and I can come with a microphone since I'm filming this.
Seems like one of the.
It seems that the mic is not working.
It's all right, all right. With autonomous vehicles in urban areas, there's been this debate of how much traffic it's going to eliminate and how much parking it can eliminate and how it can be used for access to transit nodes for sort of the last mile. One of the things that I struggle with is, and I'm wondering if you know of any models or people that have studied this, is access to curb space for pickup and drop-off at transit nodes. So for example, Delft has 100,000 people and 5,000 bicycle parking spaces at the transit node.
Yeah.
So that's 5% of the population with bicycle spots. If you were to model Delft train station, for example, with autonomous pickup and drop-off instead of bicycle pickup and drop-off, even if you did it with shared, it seems fairly impossible. So there's a lot of talk of how to deal with this curbside. I know the city of Boston is struggling with it and is about to launch a program to try to analyze that. Do you know people that are looking at that from a modeling perspective, or where you'd suggest getting started?
Yes, well, the short answer is no. Not for this specific problem. So what we've been doing ourselves, and it's the one slide I skipped, go figure, is looking at, we call it microtransit. It can be automated, it can be, well, with a chauffeur inside. It doesn't really matter for this application, in conjunction with the design of the normal public transport network. Using these type of simulations, using MudSim, actually providing some insight in what it actually would mean for the attractiveness of the system for potential travelers. So in terms of the supply side, it's a complex problem from a technical perspective, but it's doable. This element, what you're talking about, the drop-off and pick-up, we haven't really considered that yet, but actually I would not know if in MudSim that would be possible. It seems difficult, right? Because it's too microscopic, I reckon, but well, it's something definitely to consider. The other thing which I find personally very interesting is the behavioral side of things. So who will be the people that are using this system? So we've been doing some surveys ourselves, and we've been looking, for instance, at who will be the early adopters to systems like MAS, who will be the users of microtransit, and it turns out that in most cases it's the current public transport users that are going to use these autonomous vehicles instead of the car drivers. So that, in theory, would mean that you essentially get more cars instead of less, at the beginning, at least. The other thing is, what I also find striking is that we've also been looking at what autonomous driving would mean for the value of time, appreciation of people, and from the surveys that we've been collecting, it seems that that actually is going down substantially from 8 euros per hour to 5 euros per hour. If you do a projection, that could in the end mean that people will travel more. So that's more distance traveled, which essentially also mean more vehicles. I'm not going to say, well, autonomous vehicles bad. It's essentially not what I'm trying to say, but there are so many aspects that we really need to consider. Your argument is important. these arguments are important to really see what the impact will be, not only in the short run, but also in the long run. But a very interesting field, for sure, yes. Didn't really answer your question, but I've learned.
So going back to the sail event, where you have 1.5 to 2.5 million people converging on Amsterdam in a 5-day period, just wondering how much you're looping back into the planning of this event, or trying to influence the planning to make it a reasonable experience, because you can only minimize or optimize, I should say, so much.
Yeah, very good question. Thank you. This actually was the first time that we're objectively measuring numbers. So far it has been guesses, and reasonable guesses, I have to say, because they weren't so far off. But in this case, we had our counting system that actually allowed us to, and I don't think I have a picture, to give an indication, a good indication of the number of people that were visiting over the different days of the event. And that's an essential input for the planning in the next sail. Right? Still, the numbers will be different because there's many factors that will influence it, but at least we have something that we can use to feed the microscopic simulation tools that they've been using to plan the event with more accuracy than they used to. So that is definitely being fed back. And still, you need to take into consideration that there's quite some uncertainty. But now at least we have some data on the numbers, we have some data on what people actually do, how long they spend doing the different activities, et cetera, which are extremely valuable and will make the planning process much more accurate.
Can you influence the locations based upon, pinch points and other information you're gathering?
In principle, yes, we can. Yes.
Any other questions? Okay, let's thank Serge once again.
More than welcome, and thank you.